All right, so we continue to talk about CSMA. So we talked about 3 different ways to handle a situation when we need to wait. And we need to wait when we sense the channel to be busy. So we have the aggressive one, which is the persistent one, the non-aggressive one, which is the non-persistent one, and p-persistent, which trades off between these 2 extremes, and it trades off with this parameter p. When p is equal to 1, we're persistent. When p is closer to 0, we're closer to non-persistent. Okay, one can say in general for CSMA, what is the performance of it? Well, it has better throughput than ALOA, but this is only true when the A parameter is small. And A, remember that this is the normalized delay bandwidth product. Okay, so we'll see some curves about this. Okay, now a variation of CSMA is something called CSMA with collision detection. So what is that? If the medium can be sensed while transmitting, we can then detect collision in progress. Okay, so for instance, if we have CSMA and we transmit a frame here, it takes some time before it reaches its destination, right? So a blue frame could be started to be transmitted here quite legally, right? Because the node here would sense the medium as not being busy and it can start to transmit the frame here. But if the node here can monitor the medium while transmitting the blue one, it can sense the medium to see whether it's only the blue frame there or when there is a blue and red frame. So it can then, during this period, when there is a collision, detect the collision already at this time. Then we can do something smart. We can stop transmitting at this point. Collisions can be detected in the traditional way to detect a collision is that we transmit a frame and we don't get an acknowledgement. Then we assume that there has been a detection. Okay, and that takes some time. But if we have collision detection in this sense, then we can detect collisions quickly and we can more quickly recover from that. Okay. So a collision, why is that harmful? Because it implies that the frame is typically lost. This is actually not always true, but if we assume that this is the case here, then we would like to avoid collisions. And therefore, if we can detect that a collision is ongoing, what should we do then? Well, we should stop transmitting because it's meaningless to keep on transmitting. It will only waste power and time. So CSMA with collision detection works as CSMA in the beginning. So we sense the channel. If busy, then we act, persistent, non-persistent, or p-persistent, for instance. So we back off we wait according to whatever policy we have. If it's idle, what we do then is we transmit. Okay, but during transmission, we check for collisions on the medium. If a collision is detected during transmission, what we do then is we stop transmission after a short delay. So we don't stop immediately, we stop after a short delay, and I'll explain why in a second. And then we back off a random time and sense the channel again. Okay. And as we will see on the next slide, it takes about twice the propagation time before all nodes can detect a collision which is ongoing. And this time is then called the contention period, and I'll explain why in a second. Okay, so let's go through an example here and explain the basic ideas. So here we have station A, B, and C. We have time, we have space here. So the first thing to happen is that A senses the channel and it's free and then starts to transmit its frame. And the frame then reaches B at this point and C at this point. C, on the other hand, during this time, if C senses the channel, it would sense it as being idle, and it's allowed to start to transmit here. So this is what we call the vulnerable period of this protocol. It's the time where the protocol is unable to prevent a collision. Okay, and the time for this is equal to the propagation time, t-prop, because A and B are on the maximum distance from each other. So the time it takes to go from A to B is t-prop. Now, suppose C starts to transmit a frame at the very latest point it can. It's actually at this point in time, right? Because the channel is idle, and then C can start to transmit at this point. So C starts to transmit the frame, and it goes over the channel. Some millisecond or microsecond after C has started to transmit its frame, it realizes that there is a collision, because what C can see on the channel at this point in time is not only its own frame, but also something else. So it knows that the collision has occurred here. Nevertheless, C starts to keeps on transmitting a short while before aborting its frame transmission. And the reason for having a little bit of time here is to allow A to detect the collision as well. Okay, so for A, so from A's perspective, it has an idle channel and then started to transmit its frame, and then after 2 t-prop seconds, another frame arrives. So A here needs to be able to detect the collision, and it takes a little bit of time to detect the collision. So therefore, we have the rule that when you detect a collision, you don't abort the transmissions immediately. You keep on transmitting a little bit. Okay. So what happens then is that then A will stop transmitting at this point, and now the cycle is completed. Okay. So here is a collision event, and this collision event is actually the most harmful collision event in the sense that it takes the maximum time before all nodes knows that the collision has occurred. Because what happens here is that at this point in time, C knows that a collision is ongoing. At this point in time, B knows a collision is ongoing. At this point in time, C knows a collision is ongoing. And it takes about twice the propagation time, in the worst case, for all nodes to be informed of a collision that's ongoing. And then if this time is then negligible compared to the propagation time, we can say that the time it takes before all nodes on the network knows whether there is a collision or not is 2 t-prop. Okay? And this time here is then, or this interval here is called the contention period. Contention period meaning that this is the time during which nodes are competing for the medium, and after that we know that if one has won or not. Question?
Yeah, the contention period,
Mm-hmm.
now that's 2 t-prop. Is that always that? Or if we scale up the system, let's say we have 4 stations, is that still?
Yeah, so...
Or is it 3 minus 1?
Okay, very good. No, so if we introduce a node D here, nothing changes, or E here. It's still 2 times t-prop, because t-prop is the time from one end of the network to the other network. Of course, if we increase the size of the network, that is, we add more cable to it, then t-prop increases, and therefore then the contention period goes up. So the 2 here has nothing to do with the number of nodes here. It just has to go t-prop here and t-prop there. Okay. Other questions? Okay. So here, if no, the upshot of this is that if no collision is detected during the contention period, the transmitting nodes for sure that it owns the medium, right? It owns it, it has captured it, because every other node will have learned about its transmission. Okay, and there will be no collisions. So if no collision is detected during the contention period, the node that has the node which started to transmit has successfully captured the channel. Okay, it won the contention, it won the competition. Okay. And the assumption here is, of course, that the frame length here, the green part, has to be at least 2 t-prop. Okay? Otherwise, we will not be able to detect the collision. Okay? So this is actually an important design criteria, that for a certain network with a certain length, a certain propagation time, then we have a requirement that the frame length has to be at least a certain time. Okay? So we will see later on when we talk about Ethernet that this is an important thing, that there is a minimum frame length in Ethernet. Okay? You cannot transmit less than, I think, 64 bytes. That's the smallest you can have. Okay? And then there is a maximum frame size also. But it's a little bit interesting that there is a minimum frame size. Okay. So, is CSMA CD any good? Yes. So CSMA in particular is better than ALOA, except when A is very large. But how good is it? Well, it's actually rather complicated to do this analysis, so I won't do it here. I would just present the result. You can read in the book if you're interested in the details. But what we are interested in is the rho max. Okay, so that's if you remember, this is the maximum load that the system can sustain. And the maximum load, we get that by taking the throughput, the maximum throughput we can have, and divide through by R. Okay, and to get the maximum throughput, what we essentially do is that we push more and more data onto the system until the throughput peaks, and then we don't push more data. So if you remember how this looked for ALOA, then we had G and S here, and G is, and then we had some curve that the throughput goes up and then it goes down, right? And the same thing here is true in general, that it goes up and then goes down for CSMA CS. And here we can think of this as RU and instead of G. It's the same variable, but slightly different unit. Okay, so rho max is RU divided by R, and then one can show that it's actually something like this. It's 1/1 plus 2E plus 1A. And actually, and this E here is this 2.7 whatever, right? So it's E, the constant E, okay. And A here is then the normalized delay bandwidth product. So it's T-prop divided by X, where X is the frame duration. And this E here actually comes from slotted ALOA, okay, in the analysis. So if you look at the analysis, it comes from that. It's the same E that pops up there. Okay, so this is good as long as A is not so large, right? When A becomes large, then this term becomes large, and then rho max goes down. But if A is relatively small, then this is much better than ALOA, right? Remember that ALOA okay, so we can see this actually on the next slide here. So here again, if we plot rho max is the maximum load we can have. It can never be more than 1. That's the best we can do. But it can certainly become smaller. So for ALOA, regular ALOA, we know that the normalized throughput, the maximum one, was 1/2E. Okay, so it's 18%, something like that. And for slotted ALOA, we have twice of that. It's 37%. Now, if we neglect that we also need guard intervals for slotted ALOA, the throughput for slotted ALOA and unslotted ALOA does not depend on A at all. So it's a constant. So for unslotted ALOA, this is true. For slotted ALOA, this is sort of true, except when the propagation time becomes sizable compared to the frame length. Okay, but let's ignore that fact for this case. And then if we then use CSMA, then we go from here, or say we go from, so we started with ALOA, we were not happy, so we do slotted ALOA. We're still not happy, we would like to have better efficiency. Then we can go for CSMA, and suppose we use 1 persistent CSMA. then this is a sizable increase in performance. But as A increases, this one drops down, and then it's below slotted ALOA at this point, and then actually below ALOA at this point. So for large A, there is no need to go to CSMA, because we can still go with ALOA. Okay, we can improve on CSMA by having, say, a non-persistent CSMA where we optimize the p-value, and then we're up here. So this is quite good efficiency. It's closer to 80%, which is much, much better than 40%, of course. Okay, but then again, it degrades as A increases. And then if we also add collision detection to this, we increase performance a little bit more, actually. So for low A, collision detection is a good thing. But when A increases, the gain of having collision detection diminishes, and then it becomes insignificant at the end. Okay. So this curve itself somehow indicates that there are not one max scheme that's universally best, right? So which one we choose depends on the situation and also our capabilities. For low A, for sure, CSMA CD. For high A, let's go with the simple ALOA, right? Because it's the simplest. Questions? Okay. So now we will shift gears a little bit. So we still talk about medium access control. And what we have talked about now are schemes which are loosely coordinated, where the nodes, the access to the channel is not really very tightly controlled. So let's move over to another situation where we have a controller, where we do scheduling, where there is a scheme for transmitting on the medium, where we have something which is more tightly controlled. So these are called reservation systems, or one branch of scheduled access to a medium is to have what's called reservation systems. And there are two flavors of this, one which is centralized and one which is distributed. But the main idea is that we have, before transmitting frames, we agree upon in which order or how to coordinate the transmissions. So if we are all here in this room sharing a medium and we would like to transmit the information, for instance, by talking, before even talking, we agree upon in which order to do that and who should talk at what time and how long he or she should talk, right? So that's before we even start to transmit. If we did ALOA, then we would start to talk whenever we wanted to, right? And that would generate collisions. But by coordinating this, we can avoid collisions. But the coordination, the cost of coordination could be substantial, which means that it could also be inefficient. Okay, so it's sometimes good and sometimes bad to do this. Okay, but what do we do here? Well, with reservation, we have done, if we have a centralized system, we have a controller, a super user that accepts requests to send from transmissions and then issue grants to transmit. So if I would be the controller, then you request transmissions by raising your hand, and then I would acknowledge whoever is willing to want to transmit, and then that person gets to transmit, right? So that's the centralized version of it. If it's distributed, then we have some other way of coordinating ourselves. And one way to do that is we can have a token. So if I have the token, I can speak. So when I have speak, I give this to Shoaib. And if Shoaib has something to say, he speaks, and then gives over the token to the next person and so forth. This is called token ring, right? So that's a distributed way of doing it because we all pairs in that sense. Whoever has the token has temporarily the right to talk. Okay. Basic reservation system follows this mechanism that we have cycles. And the cycles consist of a reservation period where we coordinate transmissions, and then there is transmissions. And then there is a coordination period and transmissions, a coordination period and transmissions. And these cycles then can be then split out into this reservation part, which is then, we can think of that as consisting of M slots here, where we coordinate who's going to transmit. And the outcome of this coordination period then results in a schedule for when things are transmitted. Okay, so transmissions are organized in cycles, possibly of different lengths. A cycle consists of a reservation interval and then data frames. The reservation interval consists of M mini-slots in which the user reserves future slots for transmission. So, for instance, if we look at this interval here, we see that in this reservation interval, the result of the reservation interval was that 3 frames were transmitted. So 3 out of these M users had data to transmit, and they transmitted that. So for instance, say that the second, the fourth, and user number M indicated in this period we have data to transmit. And then, since they know their individual numbers, user number 2 transmits here, user number 4 transmits here, and user number M transmits here. So think of it like this, that in the beginning of the reservation interval, some of you raise your hands, and then you know in the next cycle you will transmit, and the order is then determined by your number, your ID. Right? So 1, 2, 3, 4, etc. Clear? It's pretty straightforward way to do this. So if we do decentralized, then we have a centralized controller that listens to these reservations, so listens to these transmissions, and then informs user number 2, 4, and M that they are allowed to transmit. Okay? So central control listens to the reservation, decides the order of transmission, and then issues grants to transmit. So there is some back and forth during this period. Right? Distributed, each node listens to the reservation intervals and determines its transmission slot by its relative order. Okay. This of course could be problematic when reservation transmissions are lost, and that's true for both of these cases. A reservation scheme then can allocate a single slot or multiple slots to a certain user in a cycle, right? Because it could be like you have different amounts of data to transmit. So when doing a request to transmit, you can say, well, I need 2 slots, or 3 slots, or 1 slot. That could be a part of asking the permission to transmit. So we don't necessarily have to confine it to 1 slot per user per cycle. It could be more than 1. Now, if you see in here, we have a chicken and egg problem here, and that is that we need a medium access control for the reservation interval. Right? How should we transmit here? Right? So we need to transmit here in order to coordinate the transmission here, but we need something to coordinate the transmission here. So we have a little bit of a problem here that was pushed under the rug. So let's take up the rug and see what's underneath there. So we need some medium access control for the reservation interval. And there are 2 ways to do this again. We have some random access. Maybe we do slotted ALOA in the reservation interval. Or we use some static channelization scheme, which means that, which is sort of indicated here, that if we have M users, these are pre-allocated to a slot in the reservation interval. So first user number 1 can transmit this reservation status. I'd like a frame or not a frame. In this case, no frame. Number 2 says, okay, I want 1 frame. 3 says, I don't want a frame. 4 says, I want 1 frame. And M says 1 frame. And once this is done, if this transmission is heard by everyone, they know when to transmit. Or the central controller can listen to this and say, okay, user number 2, you go first for 1 slot. User 4, you go then for 1 slot. And user M, you are last for 1 slot. Okay. Questions? Okay. If we had random access here, slotted ALOA, then basically those who were lucky enough to get their reservation frames through would also get access to the channel. Those who reservation frames got lost simply has to wait for the next reservation interval. So they got unlucky. Right. But even if we have random access here, the overall scheme is a scheduled one because we avoid collisions for the data frames, even though there are collisions for the reservation frames. Questions? Yes?
Where is this reservation done?
Where?
Yeah.
On the medium. Was that the question you had, where these physically these transmissions are done? On the medium typically. Or it could be also in some cases a specialized channel for this, radio channel for this. So for instance in GSM or something like that, there is a channel which is the random access channel where one requests permission to transmit. And then the base station allows this. But here we think of this as being, this is also transmitted on the medium. Did that answer your question? Yeah. Okay. So again, we use the medium to coordinate the medium. Okay. Is this any good? Well, let's look at this fixed channelization reservation schemes. So what does that mean? Well, it means that we have some time interval here, and then a reservation slot. We have a number of reservation slots here. Okay, and suppose we have m of those. And then we have data slots which follows this. Okay, or data frames like this. And the extent of a data frame is x seconds. And the extent of a reservation slot is some fraction of this, typically a much smaller fraction if this is going to ever be any efficient. And that fraction is nu times x. So that's the size of the mini slot. And we have the frame size x as usual. Okay, so the mini slot duration is nu times x, where x is the length of the data frame, or sometimes also called the slot. We assume that the propagation delays are negligible here for simplicity. And then we suppose that all m users have data to transmit. So actually all users said, okay, I have data to transmit, which means that the number of data frames here is m frames for data, m mini slots for reservation, and m data slots for transmission of data. So then rho max, what is that? Well, it's the data portion of a cycle divided by the cycle length. This is true in general. Okay. So this is how much data we get through, and this is how long it takes. Okay, so we have then mx frames here. We have mx of these blue frames, m of these. Okay, so the cycle length is mx is the data portion. The cycle length is the data portion mx times m times mu x, which is the reservation time. So we have mx divided by mx plus m times mu x. Questions on that formula? Okay. Data. So data, reservation. Okay. And the cycle is data plus reservation. Okay, and then we divide this through each other and we get 1 plus 1 over nu. And not very surprisingly, we get good performance when nu is small. Okay, so if it's 1%, then we get close to 1, which is what we would like to have, right? If it's equal size of the reservation interval and the data slides, if it's the length of a reservation slot is equal to the length of a data slot, then we get efficiency 1/2. Right? Half the cycle goes to data and half the cycle goes to reservation. So 1 over 1 plus 1 is 1/2. Questions? Okay. Now, suppose we, instead of having m users here transmitting data, but only capital N users transmit. So say we have 100 users attached to the medium, but only 10 of them have data to transmit. Then only 10 of them transmit, of course. What happens then to efficiency? Well, actually, the data length portion is nx now, rather than mx. So we still have nx here, but the reservation interval does not change. It's still the same, regardless of how many users that actually transmit. So if you simplify this, we get this equation, and we see that we have a problem when m is much larger than n. That is, we have few users among the whole population that has data to transmit. So if we have 100 users attached, if only one transmits, it's very inefficient, because then it could be like the reservation interval here is actually dominating the data portion. Right? If we have many users, we have a long reservation interval. But if only one of them is using have data to transmit, we only have one blue slot here. Okay, then efficiency goes down. Okay, now another tweak to this is that suppose we can reserve multiple slots for those users that have data to transmit. So suppose we transmit up to k of those. So, and suppose also that all of these n users, each of them use k slots, then the number of data frames that we have is now, instead of n, it's n times k. Okay. So even in the case where we had 100 users but only one user transmit, that user might be allowed to transmit 100 frames. Right? That could be true, right? And then the data portion is then n times k times x, and the reservation interval is the same, m times nu times x. And if we just do the calculations, we get this type of expression, and we see we get good efficiency if k times n is large or at least dominating m, right? Okay, and then rho max is then nu divided by k in this case. That is completely wrong, right? Is this wrong? This is the efficiency. Okay, so now suppose that we choose n equals to m, okay, which is the maximum we can get. Okay, then we get this. Okay, so it's actually true. Okay, so this is the best situation. Okay, questions? Okay, we continue. Now, suppose we have this random access reservation system. So that means that during the reservation interval, we use Aloha or CSMA or something like that in order to do the reservations. So what is that? Why is this good? Well, it's actually good in the situation where the idea here is that we would like to limit this interval here. So suppose we have the case where we have thousands and thousands of users, but they transmit only very seldom. Okay. Then it's a waste of time to ask each of the users whether they have data to transmit, because in 99.9% of the cases, they don't have anything to transmit. So we don't need to ask them. So rather we ask the users to be, when they have something to say, they compete for a slot in the reservation interval, and if they do, then they're allowed to transmit. Okay. So these random access reservation systems are useful when only a small fraction of the many users have data to transmit during a cycle. This is a good case for this, and there could certainly be situations where this happens, right? Where you have many nodes, but relatively little data to transmit per node. Okay. So reservation could be done with slotted Aloha, and say that we have capital N reservation slots. In the best case, we know that we can schedule n over e slots, users during the reservation interval. And why is that? Well, it's because the reservation interval here consists of n slots. Okay. And in each of these slots, there is a contention for the channel using slotted ALOA. And we know that with slotted ALOA, the throughput S max is equal to 1 over E. Okay. So in the best case, 1 over E of these slots have a clear channel, right? In all other, there will be collisions. So 1 over E, what is that? We said that that was about 0.67, something like this, wasn't it? 37, perhaps. Oops. No, I got a little bit confused about the numbers here. But anyway, so let's say here. So out of these n slots, n over e slots are actually useful in the sense that there will be no collisions in this and where we can make a reservation. Okay. So in the best case, we can schedule these number of users. Okay. And the maximum efficiency, what is that? Well, it's the number, the data portion, which follows after this. And the number of slots here is n, is the number of users we can schedule, which is n over e. So the data portion consists of, in the best case, of n over e data slots. So n over e times x is the data portion, the blue part here. And then the reservation part is n times n mini slots, which is n times nu times x. Okay, and simplifying that, we get this to be rho max. Okay, and this is quite much better than the case we would have here when we have channelization where we do reservation, where n is quite much smaller than m. So think of m as being 10,000 and m as being 1 or 2. Then the efficiency here is very, very small. Okay. So there is another way to increase the efficiency of the max scheme. Questions? No? Okay. Right. So now we've done reservation schemes, and let's see if there is another way to do this. So with reservation schemes, we divided up the medium axis into cycles, a reservation cycle and a data cycle. There are other ways to do this also, and this is something called polling. And polling is a centralized or distributed way of coordinating transmissions. So the simplest thing to think of is that we have a central controller, the green part here, which actually goes around and asks the stations whether they have data to transmit or not. So the controller first asks station number 1, do you have any data? And then station number 1 says, no, I don't, or yes, I have, and here's the data. And then the station goes and asks, the controller goes and asks station number 2, do you have any data to transmit? And says yes or no. And if it's yes, then it actually transmits its data. If it's no, it doesn't. It just sends a control message back to the controller. And it goes around here, maybe in a round robin type of situation, right? It starts with 1, 2, 3, 1, 2, 3, 1, 2, 3, etc. Could be other strategies also. Maybe 2 is more important than 1 and 3, so it goes 2, 3, 2, 1, 2, 3, 2, 1, or something like that. Okay. Distributed is where we almost have this token thing. Okay. So when I have it, I transmit. Otherwise, I give the token over to the next person. The next person, if the next person doesn't have any data, it immediately passes over the token to the third, and so forth. So that's a one of these round-robin things. So one has the token, and if it has data, it transmits, and then it hands over the token to number 2, which transmits, and so forth, and goes around. Questions? Okay. So polling variations, there are several of these. And one thing is that if a station gets the permission to transmit, it can either be allowed to transmit in an exhaustive or time-limited way. An exhaustive, it basically transmits until it has no more data to transmit. This could be problematic because if a node has a lot of data to transmit, they can occupy the medium for an extended period of time. If that is the case, then we typically limit the time for which a station can transmit. So if I have the token, I have the permission to transmit, I have a gigabyte to transmit, maybe I can only transmit 10 megabytes before handing over to the next one. Okay. So exhaustive is efficient, but it leads to long delays. Time limited is that the delays are controlled, but efficiency could be a problem because whenever I transmit, there is a certain overhead included in that. Okay, so if I can transmit a lot of data, that's generally better than to cut up the data in smaller chunks and transmit them individually. Efficiency here for these type of things are similar to reservation protocols, so there is no big difference between these. Questions? No? Okay, so let's summarize what we have talked about so far. We started by talking with ALOA, CSMA, and CSMA with collision detection. Okay. All of these are what's known as random access, medium access control methods, meaning that we don't agree, we allow for collisions to happen, basically. To be quick and fast coordination, meaning that the coordination is not perfect, right? But it's sometimes very useful. So random access is unstructured, so it's not very controlled, loosely coordinated access to the medium. There is some coordination, but it's not perfect, right? It uses collisions and randomized backoff to self-organize, if you remember. So actually, the coordination here comes from collisions. That's the way we coordinate, if one thinks about it. So it's simple and it works well, and it particularly works well when the load is low. Okay. And which means that the data rate of the medium is quite high compared to the demand for that. Delays are variable. Okay, it comes inherently in these, and unfortunately it increases with the load. So efficiency is not great for high loads. So random access, simple, uncoordinated access is pretty good as long as you don't try to push the medium to its full capacity. Scheduled access, on the other hand, structured, well-coordinated access to the medium. Problem with this is that coordination is costly because we use the medium to coordinate. Okay, and the coordination could be costly, for instance, when we have high delay bandwidth products, and it could also be complicated. I mean, it has some implementation complexity associated with it. Okay, the upshot, however, is that it can be very efficient also for high loads. Right. And delays can be controlled in a good way. It could be less variable, and we can maybe guarantee upper bounds for this. Okay. So if you remember, if you saw the lecture on traffic safety, we know that for traffic safety, delays are important, and also for network control, we know that delays are important, both the absolute delay and the jitter. So which one should we choose then if we're concerned about delays? Scheduled or random access? What should you choose? What would you choose? If delays is the only thing you care about, to control the delays. Schedule, exactly. So what is used for traffic safety? It's not the perfect choice, so there are other forces at play here, right? So what is common to use now for network controlled? Well, this is the classical way to do it, but there is a push towards this. Why? Why should we go for a worse solution? There is a
number of nodes, maybe?
no, money. Cheaper. More equipment, well understood, so forth. So unfortunately, we engineer perfect solutions, and then the finance department tells us to do something different. All right, so see you next week.